The Diekmann condensation. The Diekmann condensation is a cyclic version of the Claisen condensation. The only difference between the Claisen and the Diekmann reaction is that the Diekmann reaction occurs intermolecularly. This means that the enolate component and the carbonyl component are parts of a single larger molecule. Diekmann cyclization works best with 1,6 and 1,7 diesters to form 5 or 6-membered cyclic beta-keto esters. Like the Claisen condensation reaction, the first step in the Diekmann condensation is the addition of a base to form the enolate. Notice that there are 2 carbons in the 1,6 diester that have alpha hydrogens. Since the molecule is symmetrical, it does not matter from which carbon the hydrogen is removed. The first step is an acid-base reaction to form the ester enolate. Notice that the base is matched to the ester side chain, so that if there is an attack by the base at the carbonyl carbon, the same ester is reformed. The ester enolate is a nucleophile and will attack the electrophilic carbonyl carbon to form the cyclized tetrahedral intermediate. Loss of ethoxide forms the beta-keto ester. Both of these steps are reversible. The driving force that pushes the equilibrium to products is the next step in this reaction. The very acidic hydrogen between the 2 carbonyl groups is removed to form a resonance-stabilized anion of the beta-keto ester. The resonance-stabilized anion is the weakest base in this reaction. Thus, thermodynamically, the equilibrium is shifted to its formation. After acidic workup, protonation of the anion produces the cyclic beta-keto ester. The Diekmann reaction will also produce 6-membered cyclic beta-keto esters. Let us now also consider a non-symmetrical 1,7 diester and look at the selectivity of this reaction. Notice that in this 1,7 diester there is a methyl group bonded to one of the alpha carbons. The molecule also has alpha hydrogens on 2 different carbons that can be removed to form 2 different ester enolates. If deprotonation occurred on carbon 6, cyclization would produce a 6-membered cyclic beta-keto ester. Deprotonation could also occur on carbon 2. However, in this case, cyclization does not occur, and the production of the other possible beta-keto ester is not observed. Let's look at the mechanism to understand why only one product is formed. First, consider deprotonation at carbon 6. The base deprotonates carbon 6 and forms the ester enolate. The ester enolate then reacts with the carbonyl carbon to initially form a tetrahedral intermediate, and then reforms the carbonyl by displacing the ethoxide ion. The 6-membered ring is then readily deprotonated to form the resonance-stabilized beta-keto ester anion. The previous 2 steps in the mechanism were reversible. However, since the beta-keto ester anion is resonance-stabilized over 2 oxygen, the equilibrium now shifts towards the products. After the addition of a dilute acid, the anion is protonated to form the neutral product. Now to answer the question, why isn't there cyclization when deprotonation occurs on carbon 2? First, deprotonate the alpha carbon at carbon 2 to form the enolate, then cyclize to form the beta-keto ester. Now there is one major difference between this keto ester and the first one. This 6-membered ring does not have a hydrogen between the 2 carbonyl groups and cannot be deprotonated to form a stabilized anion. Thus, this condensation reaction is reversible. The ethoxide ion can attack the carbonyl carbon, open up the ring, and reform the ester enolate, which can then become protonated to reform the starting material. If the starting material is then deprotonated at carbon 6, the reaction will proceed to the cyclized beta-keto ester. Thus, when we have substitution on one of the alpha carbons, the reaction is selective to which way it will cyclize. The Diekmann condensation is an intermolecular cyclization reaction that works best with 1,6 and 1,7 diesters to form 5 or 6 membered cyclic beta-keto esters.